We start with a couple of things. I've got some code, and the code we'll be looking at is this right here. And we'll be reviewing some of the structures that we'll be using throughout the class. Okay. We'll be talking about how the indexing works and what is a stack. And everybody get a piece of paper. So what we'll be doing with this is we're now going to do a sort of transition from, so far we've been generating all of our assembler by using the compiler. What we'll be doing now is looking at assembler that we use, that we write in assembler. Okay, so we will be working not the rest of the semester because there's a few other things I'd like to bring out. Because technically you're not going to write in assembler. You may use the inline assembler. Did anybody stumble across that? The ASM keyword within GCC and C++? Not yet. We'll touch on that. Not tonight, but we will. So what I'm going to walk through tonight, this is in our gas format. So it's not the MASM that we've been looking at. Tonight, we'll be jumping into a different book that is in Canvas. It's called Programming from the Ground Up. And we'll be looking at the first couple of chapters. And I'm also going to be using some data from chapter 11 out of this book. Okay. To start with, let's talk about a stack. Now, how many have had 272? Okay. Oh, good percentage of you. So the idea of a stack, you know what it means. It's like a set of plates. You put it down, pop it off, you know, so last in, first out. Well, there's a stack for the program counter and things in assembler. Okay. And we have registers that we put stuff in. And this particular code will be 32-bit for the sake of argument. And I want to write a little diagram up here. You can find it. There it is. So, see if I can, is it going to show up on the whiteboard over there? Okay, so here we have our percent EAX, right? And we have this many bytes. And then we have a split. We have a percent AH and a percent AL. And these two together are called what? AX, I think, yeah. So as we move our data into these registers, you can choose what you want to move into here. So for the most part, so you can see EAX is here. It's the whole thing. It's not just part of it. Right? And each one of these registers has a break apart like this. So these registers, and we move stuff in and out of it. And what we'll be doing tonight is, as we go through this, I'll be adding some comments so we can kind of explain what this is doing. First of all, by just looking at this code, can you figure out what it's doing? Just taking a guess. Screen sharing, I think that's recording. I think, yeah, I turned off recording. And there is computer science club tonight. Okay. Now, since somebody gave you some code, type it in, see if it works. But we can do that. But just looking at the code, it's kind of hard to tell. Take a guess.
Some type of loop, I can see that.
It's a loop. That's right. There is a loop in there. And basically what this is doing is it's using assembler directives to find the maximum value. Okay. So it still doesn't make any sense because I'm looking at all this gibberish. It doesn't make any sense anyway. Okay. So what we'll be doing is let me go ahead and add some comments as we do this, and you can write it down on your paper or you can put it in however you want to do it. Because tonight, what we'll be doing is we'll be playing with this and learning how to move stuff and do things in assembler without having to use the GCC, which means it's going to strip back quite a bit of what we'll be able to do. But we still have the ability to write to a file and read from a file at a very low level. It just takes a lot more steps. Okay. So, and this is, again, this is the gas format, which is a universal assembler, but this is still separate and distinct from what the CPU needs, right? So if we were to compile it and run it and put it in the debugger, we will see the symbols that are actually being used by, if we turn the right switches, okay? So let's make this work first so you can kind of see what it does. And this is kind of how will behave itself. Csci.s, and I'll say, now if I'd named the file maximum, you probably would have figured it out. Huh? And we'll call it Csci.o. So this just assembles it. And if we do a file on Csci.o, what do we get? It's relocatable. We don't have any extra flags in there. Now I'll link it. We'll just call it Maxi. And the way this particular program runs, I'll run it separately. Whoops. LS is not what I want. There we go. So if I run this program, it didn't display anything. What happened? Ancient history. How did we get our return codes? Echo. That's right. We use that echo $? So it's returning the maximum value in our list here. Okay. Now, how is it doing this? Well, what it's doing is using a couple of these. It's using some compares and jumps. There is a sort that you probably learned is the bubble sort, right? The bubble sort is a super simple sort. And it doesn't take much to get them to work. but they're not terribly fast. Okay. But they work great. They're easy for quick and dirty things. Okay. So let's put in a few comments as we start working our way through the code here. All right, so what I will do is put some things in here at the top. Kind of explain what we're doing here. Let's see, how want I do this? Let's do it right here like this. So what this is doing is we are now using these registers are the following uses. Our EDI is holding the index of the data item being examined. Now, what is our data examined? It's in this thing called long, right? And it's got those numbers in it. So that is the index that's keeping track of where we are in our array. And notice it's ending on 0. That's the quote terminator. It doesn't have to be, but that's what it's using to check. Okay, that tells the program, hey, we're done. We're finished. Okay. And then let's add this information so we know how to make it work for future reference. But I don't know if I want to make you write assembler or not. Maybe 1 or 2 small programs that just need some modification. I think it's more important to know the inline ASM, which has a whole nother thing to it. Anyway, we'll get there. All right. Grab some paper off the back there. Yeah, okay. All right. And so this makes it work. Okay, we just did that. And let's see, memory locations. And then for our data items, what are they? It contains our data. And 0 is used to terminate. Okay. So notice this buzzword.
So you, earlier you said 0 doesn't have to be the one to terminate. What else can be used to be the terminator? In
this case, well, this is where we're going with this, is that we're putting a physical 0 in there. And that physical 0 is going to be compared. And when it gets to it and knows it's done, we could change that to something else, but then we'll have to change the condition when it's done. Since this is maximum, 0 is going to be at the bottom of the list. So putting 0 to say, hey, I'm done filling out the list. This is not the same as an ASCII or a C string, which is the null terminated string. This is just saying, hey, I got this many characters, and when you get to the 0, stop. So do you suppose we could add a few characters to this in our sort and find a maximum? Probably. Okay. So in our, let's see, data items contains our data, right? Yeah. Data, and then we simply put A, and then 0 is used to stop program. All right. So where do you, this is the data items, right? Here's the data. Data, and basically we are looking for the maximum value here. That should be maxi. So that's very good. Find the largest value should be in there somewhere. How about right here? All right, then we start with our assembler directives to tell it what to do. Okay. Now, as we do this, what did it say EDI was for? Pulls the index. Now, what happens here? It's a little confusing. So with gas, its value gets pushed into the register, right? And with MASM, it's the other way around. Okay. So I have a value of 0 that's being put into EDI. And what was the comment that I put in here? That's the index. We're starting our index. So if I was to say print data item 0, what's it going to print?
Number 0.
It's the index to data items.
Oh, okay. The first item is a list.
Yeah, it would print 3. Because that's the first value. Does everybody catch that?
Yeah.
Because we have our values that come across here. The index to get to that value, this is 0. This is 1, 2, 3, 4, 5. Just like all the other programming languages. Okay. There's a few programming languages that do not start with 0. And it will always throw you. So this is basically moving the actual 0, moving a 0 to the index. Okay. Index register, really. Okay. All right. This line, but now that I have 0 on my index, what it's doing is EAX is the current data item. So if I have an index of 0, right? What's my first data item going to be? 3. That's going to be 3. So then in this one, whoops. This actually loads the first byte of data. And then what is the data? It's actually in data items, right? And the next one is this move. Whoops, I'm going to scroll down a little bit. Whoops. So I have a move here, and I got these moves where it says L, move long, which means in our case, we're using the whole thing. Okay. And in this case, it's 32 bits because this is kind of what we're playing with here. Okay. It can be 64 or whatever. So it's now that we get our first data, now we take EAX, which is the current data item, and then we're looking for the largest data item found. We're going to put it into EBX. Okay. So we now say, all right, I've got EAX, and guess what? This is our very first thing. So of course, it's going to be moved into EBX. So what's in EBX now? 3. You tracking?
Yep.
Kind of this kind of, we're starting to see how this works. It is, but it's moving in these blocks. Okay. Would you guys rather have assembler at 8 in the morning? Some of you say yes. Yeah, I totally understand where you're coming from. I personally, I am not a morning person. So, all right. All right. Then I'll simply label this as, since this is the first one, okay. And now we drop into this loop. Okay. Now, this is a comparison. Okay. So we're doing this CMPL, which is a comparison. And where I'm pulling this information out of is the other book that I posted. And let me see if I can. Damn, there we go. All right. So at the beginning, now we know we want to go back to the end of our loop. We have these instructions, compare long 0 to EAX, and then we jump to the end of the loop. We remember from ancient history that we took a for loop and a while loop, and they're exactly the same in assembler. You may have been told that go-tos are evil. Well, in the early days of C, they had a go-to. Well, that comes directly from assembler, because that's basically what jump does. It's a go-to. You're jumping to a specific location, and then you do your thing, and then move it into the register and come back. Okay. There is local scope and global scope in assembler, but it's a little more obtuse than what you get in programming with Python or C or C++. It we'll get there. Okay. So we're saying, okay, let's compare here. And then what it's doing is it, for that compare, we're saying these are different kinds of jumps. Okay. JE is jump if the values are equal. Okay. And then loop exit, and then that's JE. I'll write them right here. And JE is jump if they're equal. And then JG is jump if the second value is greater than the first. Second one is greater than the first. And then JGE is if the second value is greater than or equal to the first value. And then obviously they reverse it. Jump if the second value is less than the first, then jump less if the second value is less than or equal to. So it's greater, equal. Well, I guess I should put that in there, JG. And jump if less, jump less than equal. Okay. So these are our jumps. And right now we have one that says jump equal. This says less than or equal. And then we jump where? Back to the late order. Okay. Now, would this make intuitive more sense if I just said, type this in and put it in the debugger? Probably, because you're comfortable with the debugger to a point and you can kind of see what's happening. We'll get there. Okay. But this is actually writing an assembler. Okay, and you can change the syntax around. And I don't know if I've got the tools installed on the Jeremy box, but they're out there somewhere where you can convert from gas to Intel and Intel back to gas. They don't always work the way you expect them to. So caveat emptor, they do have that capability. And that's one of the things we will do, maybe tonight or not, is convert this into MASM. And then you can choose which one is easier for you to read, because the flags now. Hey, I want to look at that gas. You leave the Intel MASM off, or MASM Intel, and then you get gas. Okay. All right. If you are going to do kernel code and you're going to write kernel code, you're going to be using gas. Okay. So if you think you want to write kernel code for the Linux kernel, yeah, gas is the one you want to learn. Okay. All right. Then start loop obviously starts a loop. Okay. And then right before loop exit here, let's add that line in here. And this is check to see if we have hit the end. And what is end? Bingo. So you're seeing how this is working by moving it around in these registers, because we have been visualizing our gas/MASM throughout the semester, looking at it, but don't really know how it works. Well, now we're getting into the point where we're learning how it works. And the way it works as assembler is it's always a top-down flow. You're going to have jumps, there's loops, but it's a top-down flow. And you can do some tricky things with objects. And this book shows you how objects work in assembler. And it's way far in the back of the book. It is rather obtuse, but if you want to see what's really going on, it's just a re-representation of the same old, same old. Okay. All right. And then down here in the loop, this is the guts of the loop here. Sure, I've got it in the right places. We have the next value is right here. What's this INCL?
It's an increment.
Exactly. And this is basically loading the next value. Now, is the next value in EDI, that is what? It's the index. So when we say next value, it will be 1. It's going to point to our thing, and it'll be 67, 2, and so on and so forth. Okay, seeing that. Okay, good. Load next value. And then we do some compares. We move that data items. Notice how it's plural. Why is there a 4 there? It's always 4. This is how many have heard the term offset? It registers and offsets. Okay. This is exactly where it fits into is, let's go. It's not going back. It's just we never really went over it. let's start with a rather simple example. I've got post office boxes and they're labeled 1 through 10. If I want one of them, I just go 1, 10. But if I have a bunch of bits stored in an 8-bit register, and let's just call it 1, 2, 3, 4, 5, 6, 7, 8. And then I have another register with another 8 bits. My offset, this would be 0, 0, 0, and I'll use physical 1 just to make it sense here. So if I go to 0, yeah, I'll use 0, 0, why not? So this is 0, 1, 2. This is the index, right? Well, I want to load another 8 bits. What does my address start with? Yeah, it's going to be incremented as. That's the offset. This is the address pointers to the offset. That might be wrong. To the offset. So when I say, give me the offset and then the address, it goes to the right place. This is how, you're going, why does that mean anything to me? Well, I'll show you. See those funny looking numbers? Those are inodes. That's where it is on disk. It's telling me that I have this. It starts at 27, 52, 53, 59. And that's the pointer to the beginning of the file. The next inode is the pointer to the beginning of that file. And so on. This is the offset. That's kind of how you look at these things. Is you have your address, and then the offset is. You used to have to know this when you did when you put in a new hard drive. A new hard drive would have bad spots, and you actually had to type in the bad spots on the hard drive into a table so it wouldn't use that spot on disk. Well, now that's all done automatically and you don't have to mess with it. Okay. Yay, right? All right. So we have data items 4. That's what this is. This is the offset to go to the next chunk. So I could say, what would happen if I said my offset was different? I said 2 or 4. I'm not on a boundary anymore. It's like, oh, I might get some headaches. Okay. All right. So move my data items here. And then the compare down here, right here. This is comparing the values. And then what we do.
The offset is 4 bytes then.
Yeah, you catch that? It's for bytes, not bits. All right, down here. Compare the values. That's what that's doing. And then this is a jump less than or equal. That says jump to loop beginning if the new one is less than or equal to, right? Because we're trying to find the highest value. Okay. I'll just say less than or equal to. Okay. After this, before loop exit. Okay. Here we go. Let's add some here. If one value in binary. And right here, let's say this one is $sign EBX. So this is the return value. If is the number. And then down here, move one. I guess that should be on the other line. Hold on a second. Yeah. So moving one into EAX will terminate your program. Okay, that's how we do it. And then this interrupt 80 is the system call. So when you say move one into my interrupt 80, it says exit the program. So if we looked at some of our code that we did in like our foo H and everything, and we did the echo dollar number, this is what it was doing. Okay, this is where you were changing this value to other things, but it was still exiting the program because it ran out of program. Okay. So now that we've got this, we've got some labels here. Now, it goes on in there. We need to start talking about how we get to our different types of addresses. Okay. Now let's talk about our addressing modes, as we call them. Okay. So where should I put this? Now I'll just put it right in the code. I'll put it right up here at the top. So I'm adding some data that's not, or comments that are not necessarily related to what this code does. It's just stuff, okay? So let's look at, let's see, maybe I can do it that way. Let's see here. Yeah, that's good cheap. So we will continue on with this to some extent. Well, sort of. We'll go back and revisit that one. Let's see. This one. Here we go. The general form of a memory address is this. Okay. Maybe I'll put it at the bottom. Let's just do that. No. So, general. So we have an address or its offset, the base or the offset, and then the index where it goes, and then the multiplier. Okay. Now, all the fields are optional, but let's look at what this will return to us here. So our final address is the combination of these. Okay? And it goes with this information. Okay, so we have our index and we're moving things around. All right. This is, we have what we were exploring here is direct access here. I'm directly putting information into the register. Then we have indexing, which is what we did here. Okay. And then indirect is using, well, we don't have an example there. And then base pointers, that's a different thing. Pointers. If you took Java, you didn't get pointers in 271. If you took C++, they kind of did this hop, skip, and a jump over pointers. But pointers in C are a thing. The way they work is when you have a pointer. Now the syntax is really gnarly, and I don't remember it all. In C, it gives you the ability to point using a pointer to two values and then do the arithmetic and then change the values in memory. Okay, so if I have a pointer that's going to 7 and a pointer that's going to number 8, I can actually have a pointer that goes to the result where I'm actually running the calculation on the pointer addresses and it puts the result into the pointer. So I can do all my arithmetic with the pointers. I can also do other things with pointer. Now, why is this important? Well, it works with this offset that we just put in here. This is what pointers do. they give you the ability to say, hey, just go there. I don't have to sit there and iterate through things. I can just go find it.
You've been doing Go lately, right? You can explain it from the Go point of view as well. They use pointers.
Oh, Go does. Oh, that's good to know. I didn't know that. I've been playing with Go a little bit. I didn't know they use pointers. I
Yeah.
know it's not objects,
Star and ands, just like it's like in C.
just like in C.
Yeah.
Yeah, the guy that helped design Go helped
Yes.
design
Yes.
C
And
back, and he was an intern underneath Kernan and Ritchie. His name is Rob Pike. And I met him at a Google conference. He's a very interesting little character. He's very intense, little short guy, big round glasses. He looks like he's looking right through you. He probably is. It's quite a character. Okay. But those are the registers, and we're going to pick up on this as, oh no, we're not. I still have another arc. Good. As we work through this, we will be playing with how these registers behave or not. Okay. All right. Now, where am I pulling this information? In Canvas, you have another book. It's called Programming from the Ground Up. Okay. And it's basically teaching you assembler from the ground up. By the time I'm using some stuff out of chapter 3, by the time we're in chapter 4, we are actually writing functions in assembler. So it moves really fast. But we're not going to do a lot of that, but there's enough in here that learning how to write just straight assembler code. What do we need to do when we need to do a system call to do a write to disk without all the C headers? How do we do that with interrupt 80? And which system calls go to what? Okay, that's kind of where we're going. Okay, eventually. All right. Indexing. And then okay. Here we go. Some review. We should all know the answers to these questions. What does it mean if a line in the program, we're talking .s here, starts with the pound sign? Yeah, we should all know that pound sign. Yeah. What's the difference between an assembly language file and an object code file?
Object is locatable.
Right, the actual results, if I do file on maxi.s, it says text, human readable. Maxi O, it says it's something I can't look at. Okay, I can do XDD and look at it that way. Whoops, maybe I don't have it installed. Oh, I meant XXD. So that's what it looks like in hex, give or take. Okay. And it starts with ELF. This is important. This XXD, I do need to show you this. Let me pop up a Windows. And it might be a little hard to see. Yeah, figures. I know it's installed. Oh, I know I can do it. Yeah. DR, there we go. All right, let's go to program files. And let's go to what? Let's go to Vim. See those exe files?
Yeah.
those exe files. Watch what happens here. Let's bring up, well, I could do it that way. Let's use T. So I just took t.exe and dumped it to hex using XXD from the Vim tools. And I keep going up here to the top, may have to go 500 miles here. This T was bigger than I thought. Yep, we got it. There we go. NZ. Anybody want to take a guess what NZ stands for in Windows? Quick, do a Wikipedia. Why do Windows executables start with MZ?
What happens if you run that in DOS?
Uh,
It tells you it can't be ran in DOS.
it will probably just give you an error.
But that's what the header there was, that down there,
Yeah,
that when you run it in DOS, it tells you that.
it says you can't do that. But what does that MZ mean? Can we find it?
Yeah.
What's it?
I think they think it's the initials.
The initials of the guys that came up with the idea of making the compiler work. And he's living on in infamy. And DOS compiler, if it's an executable, it starts with an MZ. Just like we have an ELF, it starts with ELF. And other architectures will have different tags at the beginning of their executables, so they know which hardware it's running on. Okay, so, and I can't remember what the guy's name was, but it was like Michael
Mark Zabowski.
Zabowski, yeah, or something like that. It was, so there's another piece of that ancient trivia buried into the bowels of the systems that you never knew was there. Well, it's there. Okay, and there's a lot of weird stuff like that in this business.
At least ELF stands for something.
It does, extended Linux format.
Yeah.
Yeah. And if you remember the very, very early editions of Linux, it was in a different format. And then we moved to better hardware, 32-bit, 64-bit, they had to change all of that. So it was a big migration headache to move from one, because you actually had to recompile everything. So if you brought an application over, it wouldn't work. You actually had to find the source code to recompile it to run it on the new stuff. Like these are all Linux boxes. So if you wrote an executable and you copied it to another machine, it's going to work because it's the same hardware and it's the same operating system. Can you run a Windows binary on Linux? Trick question, but not natively. There's something called Wine, which is an emulator. It's kind of a thunking
Mine
layer.
is not an emulator.
Yeah,
It's-
Windows is not an emulator. Yeah, that's like SAN or the scanning, the scanner. What do they call it? The scanning interface is what do they call it? Scanner without a name or something like that. It was a standard that they used to move your raw data from your scanner into your system. It was called the standard without a name.
Yeah.
And that's what it was called because they didn't have a name for it. So they just called it that. And it became the de facto standard. And if you do C coding, there is a module called create, but it's missing the second E in the spelling. And this is in the book of Kernan and Ritchie when they designed C. Why did you leave the second E off? Well, the terminal I had a broken E key and I couldn't type the E as often as I needed to. So I didn't. If I was to do it over again, I'd probably put the E in there. So you will find things like that throughout. And you'll develop a library of this trivia just because it's fun. And you're going, oh, that's interesting. I didn't think of that. Okay. So what I want to do now is kind of jump back a bit into our book here. And let me find that section. All right. That's what I want. All right. This is another way to describe how we will do some addressing. Okay. So what I will do here is I'll use VI and I'm going to create a very simple customer record. Okay. So I'll just call it customer1.txt. And VI is telling me where I have my characters. Okay. So let's go to, so this is I can put anything in here I want. So let's do that. Let's start with the C name for the customer name. Okay. And I want to attribute 50 bytes. Okay. And in this case, I'll just go over here to 50. See the line there? And on line 51, I'll just put in a vertical bar. Okay. That's all I'm doing is that I'm putting in a customer record and a bunch of blank spaces, which are officially 20 in hex, not zeros. Okay. And then I'll say customer address. And again, that'll be 50. And then just for fun, we'll say customer's age. Okay. And what are we going to use here? Let's use, that was 4, right? 1, 2, 3, 4. Yep. So I have basically 50 and 50 and 1. Now, is this how the data is actually going to be represented when you look at it on a disk file? Now, it's going to look something like this. And depending on what, well, for the sake of argument, we'll just keep it the same. 50 is where I want it. So 51 is where that goes. Address, I'll just say 435. Age, 115. Old. Okay. Now, I'll use the terminating character here. Let me expand this out a little bit. I'll use a few VI tools here. And give it. Maybe you're not 115. How about, I don't know, 25. And we got like 6 Zacharys in this class. I'll just see that. You can kind of see where I'm going with this. It's just some records, okay? Now, let's make sure we get them all lined up here. This is how it's actually stored when you're in a database. Watch what happens here. One big long line. How do I get the first name out of this? I have to keep track of how far it is in each record, right? So I've got Dale is the first 4 bytes, and then the next one is going to have a rather long offset, right? Because it has to go all the way down to the next record, which is 50 plus 50 plus 4. That's where Kevin started. That making sense? That's the address scheme. That's what offset is all about. Okay. And wrapping your brain around this is how you get to things in your program. Okay. And I'll just right next to that. Okay. So if I was to look at that in hex, okay, I can see that I need to go. Oh, notice there's the addresses in hex of my file, and it's offset. So I've got there in 10, it's in hex. So it's going over. You kind of see how that's working. Now let me just change the file back to what it was. So a little more human readable. Whoa, too fast. There we go. So now we can see the file a little cleaner. But when I run it through the same tool, I'm still going to get these offsets. So you can kind of see how we get into, how we find our information using the indexes. Okay. So this is what we did. And we were having some fun down here of the general form of a memory address. And that's what we just went through. Okay. So we run this and we know it returns the highest number. Okay. What would happen if we just add a few more random numbers in here? And recompile it, or assemble, I guess. Whoops. Where did I do that? Where did I put the typo?
All the way at the bottom on line 45. All the way towards the bottom.
Pardon?
All the way towards the bottom on line
Oh.
45.
Oh, there it is. Sure enough. Thank you. LD. Call it the same thing. Maybe not. And then how do I display the result?
That goes.
Echo, all right. Still worked, even though I added characters. Okay. Now, in this book, programming from the ground up. Here's some really good questions at the end of chapter 3 that you should all be able to answer closely, maybe not 100%. And you're going, oh, wait a minute, I don't know that one. Oh, I don't know that one. Or I do know that. This is why I'm bringing this book out, because this book is actually, we will write a couple of assembler programs and we'll make them work. Okay. Pure assembler. No cheating with the C and everything else. So you can actually say, yeah, I know enough assembler to be able to read it, and that's about it. Okay. And I won't spend a lot of time doing pure assembler. The other part that we will get to is GCC inline ASM example. And it shows you how to. Let's see, basic inline. That's it. But there are caveats to this inline assembler in your C code. What does that do to your C code? It makes it bound to that hardware. So if I take C and compile it with inline assembler, it won't work on MIPS or ARM. Okay, it kind of puts a kibosh on that. So it shows you the basics of what this is. And this is the syntax that gets weird. That right there, equals R and R. That is how we do the input output by way of the interrupt. Okay. We might do one little thing in inline assembler. We won't do a lot. Just enough to know that you know it's there. Okay. Because this, if you do assembler and you are writing device drivers, this is probably more likely of what you're going to see. Okay. Rather than just long lines of assembler. So we'll get to that one. Okay. So here we go. What's the linker do? The linker does that magic to take our relocatable and turn it into an executable. And one of the things it does, it labels it as the right format, in our case, ELF. Okay. How do you check the status code? We just did it. Echo dollar question. Yeah. The difference between these. The first one is we are moving one into EAX. Okay. And then the second one is, oh, wait a minute. What is the difference between using the dollar and not dollar? Pardon? The address.
Oh, the ad.
Yeah. Which register holds a system call number? We actually type that in our comments. Okay. Their index is used for. Why do they start at 0? Some crazy piece of history. Who knows? If I issued these following commands, what would be the next one? Yeah, this is going to be really fun. Yeah, I think I better assign this to you. So just to answer the questions in chapter 3, in programming from the ground up. Okay. And we won't worry about going further. And then this is really fun little things for you to play with. I'm not going to ask you to do it. But How do we do that? How do we make it 255 instead of 0? How do I use an ending address rather than the number 0? Okay. If you read through chapters 1, 2, and 3, they're not very long. Let's see here. How many pages is it? 33 pages. If you include the very front, that includes the title page and the, so not very many. Okay. So I will post this and say, please answer the questions from chapter 3 in programming from the ground up. And just copy them out of the book, paste them into Word, type in the answers, push them up. Okay. Not too hard. And I guess I should challenge you and say, who wants extra credit? And those are always fun. So this will be extra credit here to use the concepts. Okay. Well, this you've already done. Remember? Maybe. Yeah. Maximum defined minimum instead. Where would we change that? In the compare. Yeah. I would encourage you to do this because even though you may never use this again, it's going to make your brain work in a slightly different way. And this is what I can tell you about programming is it uses both sides of the brain, both creative and logical. And there's a book called 7 Languages in 7 Weeks, where you spend a week in a new language. And what that does is it makes you a better programmer in your primary language because you learn how to see problems through a different lens. Okay. It's like learning, if you speak more than one language, you think in different terms too. Okay. All right. So have some fun with this and play with the code that we were tinkering with and see if you can answer a couple of these at the end here. What do I need to do to change maximum to minimum? What do I need to do? How do I do it? Okay. And I'll give you 20 minutes or so. Go ahead and use the rest of the class for this. Computer Science Club is meeting in here. So, and then I will post an assignment for the questions and extra credit for use the concepts. Okay.
USB in mine, PC, so
Oh.
the Linux class.
Oh, from last week?
Yeah.
Or,
I
yeah,
don't know, it was
okay.
just in there, I just noticed it. Also,
Okay.
do we need to hang on to this if we pre-typed it into the?
Oh, you just keep it. Yeah,
Okay.
type it in and play with it.
Because if I
It's also-
pre-typed it, I could probably just toss it, is that right?
Part,
If I typed it up, can I just toss it? Cause I have it
Yeah.
online, okay.
yeah, it's online. You don't have to type it. It's in the programming from the ground up. I don't know, page 20 or so.
Cool, because instead of pulling out a pencil and writing it all, I just put it in, like, with comments and like.
That's
the
fine.
way you did.
That's fine.
Is that a
All right, I'll
SanDisk?
see you next week.
Yeah, you bet.
Is that a SanDisk?
Yeah. Is it yours?
Yeah.
Oh,
I found it then.
And. If I-
oh, from last week?
Yeah, so I left I ended up getting it, my charger.
Oh,
somebody let me in.
okay. Yeah, there's a floating around here. There is an Air iPod earbud floating around that one of my students lost it Tuesday night. So if you see it laying around, put it up here on the front. Yeah. please.